For centuries, humans viewed the solar system as a perfect mechanism, planets orbiting the sun like gears in a finely tuned celestial clock. But discoveries made in recent decades, especially from missions like Messenger, have shattered that old illusion. What we now understand is far more chaotic. Mercury's eccentric orbit, chemical anomalies, and iron-rich core all point to a past shaped by violent disruptions and cosmic chance. The long-standing assumption was that the planets had always orbited the Sun in their current positions, with only minor fluctuations. But as scientists examine Mercury's composition, especially its unexpectedly high levels of volatile elements like potassium and sulfur, it became clear that the planet likely did not form so close to the Sun. These volatile elements should have been vaporized during Mercury's formation if it had originated in such an intensely heated region. Their presence hints at an origin further out in the solar system. This theory gains weight when combined with orbital mechanics and gravitational modeling. Researchers now believe that in the early solar system, planetary orbits were far more unstable than today. As the rocky planets were forming, they were surrounded by countless planetary embryos, moon-sized bodies formed from leftover debris. These bodies frequently collided, merged, or were ejected from the system altogether. Amid this chaos, Mercury's journey may have taken it from a stable, temperate zone, possibly even beyond Earth's current orbit, into the scorching inner solar system. And the force behind this dramatic relocation? Jupiter. Jupiter, the solar system's largest and oldest planet, exerts enormous gravitational influence. As it migrated slightly inward and then outward during the early years of the solar system, it likely disturbed the orbits of nearby forming planets. One of the victims of this gravitational disruption may have been the infant Mercury. Computer models simulate a scenario where Jupiter's shift alters the orbits of nearby planetary embryos, causing them to crash into one another or be flung toward the Sun. Mercury may have been one such casualty, thrown on an inward spiral where it ultimately collided with another young planet. The collision stripped away Mercury's outer layers, leaving behind a dense metallic core and an eccentric orbit forever marked by its traumatic past. This history not only explains Mercury's strange features, but also reinforces a deeper understanding of planetary migration, a concept once thought implausible. We now know that planetary systems are not fixed in time or space. Planets can move drastically during their youth, driven by gravitational interplay, collisions, and chaos. What we see today in our night sky is a snapshot of a long, tumultuous process of evolution and destruction. The implications are profound. If Mercury could form farther from the Sun and be hurled inward, then other planets, perhaps even Earth, may also have experienced significant migrations. This shifts how we think about habitability and planetary stability. It means that being in the Goldilocks zone may be a temporary condition, not a permanent feature. At Infinity Beyond, these ideas fuel an exciting narrative. The solar system is not a serene dance of planets, but a battlefield of gravity, heat, and chance. Every world bears scars of this ancient chaos, and Mercury wears them most vividly. It is a testament to the fact that even small worlds, seemingly static and insignificant, can have the most dramatic and violent backstories. As our exploration tools grow more advanced, we may yet discover more secrets locked in Mercury's strange orbit and metallic heart. For now, it stands as the solar system's ultimate survivor, bruised, battered, but still orbiting, whispering stories of a time when the heavens themselves were in flux. In the early days of planetary science, models of the solar system treated it like a perfectly balanced equation. One star, a set number of planets, each tracing a precise and eternal path around the Sun. But as the field matured, this simplistic view gave way to something far more complex and dynamic. Thanks in large part to mathematical modeling and space exploration data, we now understand that the solar system behaves more like a chaotic system, one where tiny changes can create enormous and unpredictable outcomes over time. At the heart of this transformation in understanding lies a basic principle of physics, the n-body problem. In a simplified system with only one planet orbiting a star, it's relatively easy to predict the future path of that planet using Newton's laws of motion and gravitation. But once you introduce a second or third planet, the problem becomes exponentially more complicated. The gravitational interactions between multiple bodies, such as Mercury, the Sun, and Jupiter, produce outcomes that can no longer be predicted with absolute certainty. Instead, we enter the realm of chaos theory. This concept of orbital chaos is crucial to explaining the strange journey of Mercury. If it had remained in a stable, solitary orbit, its current position and composition would make no sense. But in a solar system filled with gravitational tugs and nudges from massive planets like Jupiter and Saturn, Mercury's path could easily have been altered, not once, but many times over millions of years. What Infinity Beyond highlights through data from missions like Messenger is that Mercury may have formed far from its current location. In the early solar system, it likely occupied a cooler, more temperate region, perhaps beyond Earth's orbit. In this more distant neighborhood, volatile elements like sulfur and potassium could have survived the formation process, becoming embedded in Mercury's crust. Then, through a series of gravitational perturbations, its orbit may have gradually, or even abruptly, shifted inward. Such movements are not just theoretical, they're supported by complex simulations of early solar system evolution. These models demonstrate how planets can be nudged by passing debris, minor interactions with other planets, or even large-scale migrations caused by the movement of gas giants like Jupiter. One particularly dramatic theory proposes that after being flung inward, Mercury collided with a planetary embryo of similar size. The resulting impact stripped Mercury of its lighter rocky layers, leaving behind the iron-heavy core we see today. This would also explain its highly elliptical orbit, far more stretched out than that of any other planet in the solar system. Today, Mercury's orbit is so eccentric that its distance from the Sun varies by tens of millions of kilometers during each revolution. This variation causes dramatic changes in surface temperature and affects the way the Sun appears in Mercury's sky, growing larger and smaller over the course of its orbit, sometimes even appearing to reverse direction. What's even more fascinating is that this unpredictability isn't just a relic of the past. Mercury's orbit continues to be influenced by the gravitational pull of other planets, making its long-term path difficult to predict with high precision. Over spans of millions or billions of years, these subtle forces could cause Mercury's orbit to shift again, potentially destabilizing nearby orbits or even creating conditions for future planetary collisions. From the perspective of Infinity Beyond, Mercury is not merely a battered relic from the dawn of the solar system. It is a vivid illustration of how chaos, rather than order, shaped our celestial neighborhood. Its current orbit, composition, and density all point to a dramatic past marked by migration, impact, and instability. In many ways, Mercury is the planetary equivalent of a survivor, having endured the worst the early solar system had to offer, and emerging as a testament to resilience amid cosmic upheaval.